Welcome back to my channel. My name is Dr. Arzu Chabra. I have a PhD in organic chemistry. I am a organic chemistry tutor and also a mindset academic coach for college students. I have students who are overwhelmed and who are stressed out about college or even taking MCAT, help them feel more excited, and I also help them take better control of their energy and their time. So in this series of videos, we are actually going over the Kaplan problems. So today we are actually solving the chapter Amines. We are working on the problem set for chapter Amines, and so let's get started in a second here. And so now I have shared the problem sets. And of course, if you want to download the PDF of this document, which is just like Kaplan edition problem sets, I think I'm not 100% sure the edition of the text I'm using, but I think this is 2122 if I'm not mistaken. Okay, so let's get going. The first problem is a compound with the general formula R4N plus X minus is classified as a quaternary ammonium salt, which is pretty straightforward. It's not primary, secondary, tertiary. It's actually connected to 4 other carbons, and a compound, nitrogen or a carbon connected to 4 other, would be called quaternary, right? And the fact that it's nitrogen, cation, anion, therefore it's actually a salt. Okay, amines have lower boiling points than corresponding alcohols because they have higher molecular weights. Okay, they form stronger hydrogen bonds. If they were to form stronger hydrogen bonds, then they would have had higher boiling point, right? Because boiling point is actually a function of the strength of the intermolecular forces, right? Boiling point is directly proportional to the strength of intermolecular forces. And so if your molecular forces are stronger, they'll have the corresponding compound will have a higher boiling point, right? So we can say that because amines have a lower boiling point, it is because they form a weaker hydrogen bond. All right. Whoops. All right, okay. It just like brushed to the last page. Third problem. Which of the following would be formed if methyl bromide were reacted with phthalimide and followed by hydrolysis with aqueous base? So phthalimide, right, is actually a reaction of phthalimide. Right, is methyl bromide, is the Gabriel synthesis, right? The Gabriel phthalimide synthesis. So it first forms methylated phthalimide, right? That's the first step. And then when it undergoes hydrolysis with an aqueous base, then we actually form a carboxylic acid, or more like a dicarboxylic acid. And I think this is succinamide. Yes, this is called succinamide. So we form succinamide plus primary amine, NH3, NH2, right? So this part of the molecules breaks off and it just forms CH3, NH2, okay? All right, so CH3NH2, option B is the correct answer for this problem. Okay. The reaction of benzamide with lithium aluminum hydride yields which of the following compounds? The reaction with benzamide or benzamide, right? Let's first think about what a benzamide is. So this is benzamide. The reaction of benzamide or benzamide with lithium aluminum hydride. So we are using a reducing agent, which is lithium aluminum hydride. So that would actually convert that to a benzylamine. So the C double bond O will actually get converted to a hydrogen here and a hydrogen here. So we got CH2, NH2. So we've got benzylamine, the option C. Okay, which of the following amine has a highest boiling point? Like we said earlier, the strength of the boiling point is directly proportional to, the boiling point is directly proportional to the strength of hydrogen bonding, right? So if we look at these compounds here, the strongest boiling point here that we actually see is coming from option B, because the more branched the structure is, the lower the boiling point. So we see branching over at option D, right? And longer the carbon chain, more the van der Waals forces, right? And the more the van der Waals forces, then the strength of the forces increase because they're just like more in number, but they have to be in straight chain as well. And that's why option B is actually the correct answer for this problem. Okay. If 2-amino-3-methylbutane were treated with excess of methyl iodide, okay, so we have 2-amino-3-methylbutane, 1, 2, 3, 4. So you have 2-amino, okay, 3-methyl butane, right? So we have 4 carbons in total who are treated with excess of methyl iodide, right? So excess of methyl iodide, the reaction, we would actually then form 1, 2, 3. So we have the CH3 over here. So then we would actually form nitrogen, okay? And if you're doing the methylation, it's in excess. So we can do 1, 2, 3 methylation actually, because nitrogen has like one lone pair, right? And it has 2 hydrogens. So we can replace those hydrogens with methyl and also carry out another methylation. So we can create a quaternary ammonium salt, right? And then in the next step, we are reacting this with silver oxide. So we have Ag2O and water, okay? So then what would be the major product of the reaction? So this is a elimination reaction setup, right? The important thing to remember is that in this reaction, so this reaction is more like a reaction where we more or less carry out an elimination, but however, in this elimination, it looks like an E2 mechanism, right? That the base will come over here, grab this proton, or the base would come over here, grab that proton, put the electrons back in the bond, kick out the leaving group. However, you have to remember that in this methylation or in this elimination, the reaction always is a reaction which is similar to if the base was a bulky base, or in other words, in this reaction, this is more like a reaction where a Hoffman product would be a more stable product in the reaction. So the alkene that would be formed on the less hindered hydrogen, the less hindered alpha hydrogen. So we've got that hydrogen, and then we have, or actually, instead of this hydrogen over here, so that then is a double bond over here actually is the major product of the reaction. So this is what you have to remember, that in this elimination reaction, a Hoffman product is always like the major product of the reaction. So then this is the product. Okay, and if you think about it, so plus triethylamine, okay, right? Trimethylamine, so which is in option B and C. trimethylamine, and then the third is 3-methyl 1-butene. So if you think about it, 1, 2, 3, 4. So it is 3-methyl 1-butene. So we've got option B then, being the correct answer in this problem. Nylon polyamide is produced from hexane diamine. Okay, we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, hexane diamine. So we have an amine here, and then we have an amine over on that side. So they're producing nylon from the starting material and reacting that with a substance X. And so the substance X is most probably what? So the substance X most probably is. So what, if you really think about what a nylon is, right? So nylon is an amide, right? And amide is usually formed by an amine and a carboxylic acid. So option B then is the correct answer. What is the IUPAC name for the following compound? It's also a really good problem because when I was looking at this problem, right, they're really making sure that if you're actually paying attention to details or not, right? So for N-dimethylaminopyridine, right, which kind of makes sense, N-dimethylaminopyridine, and add the fourth carbon, yes. Dimethylaminopyridine, a second option, where they don't really mention anything about the number, and that's the problem. For an N-dimethylaminopyridine, and actually when we really talk about a tertiary amine, or so this is a tertiary amine, right? So when there are two substituents present at that nitrogen, it has to be labeled with N, N. So it would actually be N-dimethylaminopyridine. And the next option is N, N. And of course, so we have to make sure we are writing N, N, right? Because there are two substituents on this nitrogen. And then at the same time, where is this substituent present, right? You have to, you want to make sure that the reader knows that too. So this is 1, 2, 3, 4. So then of course you can go over here and you can go over here too. So N, N dimethylaminopyridine at the fourth carbon of that pyridine, 1, 2, 3, 4 is the correct nomenclature for this problem. Okay. Pyrrolidine is an excellent base with pKa of 11.27. Okay. Which pyrrole, okay, we're talking about here. Pyrrole, no, I'm sorry. Actually, we're just talking about this structure. Pyrrole, which has a similar structure, is a poor base, right? Which has a pKa of 0.4. Why is pyrrole such a poor base compared to pyrrolidine? So why is this a bad base? Is what they're talking about. Never mind. You know what? I'm just a little bit under the weather today. It's making me really, it's really not helping my brains today. So why is this a bad base? Why is pyrrole such a bad base? Right, and the answer is actually there are lone pair of electrons. They're introducing a little bit of aromaticity over here. So at the aromatic compound, those electrons are actually involved in the ring current. They're involved in aromaticity. That's why it's a bad base, right? However, for these electrons, they are so it's a bad base and a good acid. However, these electrons are actually better donors because they're not involved in the aromaticity. They're not actually involved within the ring current. That is why it can be donated better. So it's a really good base and a really weak acid. So the answer is aromaticity, right? Aromaticity creates the total difference. Pyrrolidine is anti-aromatic. It's actually not aromatic. So pyrrole is aromatic is the correct answer. Nitrogen atom in pyrrole does not have any lone pair of electrons. That's also not true. Nitrogen in pyrrolidine contains an extra lone pair, also not true. Okay. What product is formed from the following reaction? So what we really see here is a secondary amine, right? And also a cyclic secondary amine. So on the cyclic secondary amine, really what we actually have is CH3I excess, right? When I don't even remember when I was growing up and when I learned science, I don't remember if excess was actually abbreviated like that, right? I think I always saw it written like this, but nowadays it's like XS, excess. That's fun. It's really fun. But it might have been, I don't think I remember that actually, seeing it that way. Okay, so if you're doing it in excess, it's like that methylation reaction. I'm pretty sure it's followed by elimination, right? Of course. So this is the positive charge over here. So that is like the first step of the reaction. So we have methyl with the positive charge, right? And now the second step is elimination. And so if you're carrying out the elimination, right? Again, we said that less substituted hydrogen would be eliminated, but we don't really have any different hydrogens. They both are really the same. And actually, we're actually really talking about this hydrogen and this hydrogen, right? So if I carry out the elimination, the electrons will fall off here, right? The electrons fall off here, and then the electrons in this bond fall off on the nitrogen to neutralize that nitrogen. So now the product will actually look like this for this reaction, right? And that actually is option A. Okay, so we got option A as the correct answer for this problem. And so that was the end of all the problems for the chapter amines. Tomorrow I'll be going over carboxylic acid derivatives. Oh, I think I've done that already. Oh, carbohydrates is something that I'll be going over next time. Until then, keep watching and keep growing. And if you have any questions, if you don't understand anything, if you want me to go over something in more detail, or if you want me to read you something, ask a question, feel free to leave that in the comment section. I'd be very happy to interact with you guys. And if you're getting any value, feel free to subscribe this channel. If you truly feel like, you are getting the value, if you come back here and really try to learn something here, go ahead and give it a subscribe. If not, it's totally fine. And we'll see you guys next time. Bye now. Have a great rest of your day.